Okay, great. Let's start. Hello, everybody. So today the plan is to continue discussion about MIPS assembly. Some more maybe somehow advanced topics, kind of advanced constructs that we can use in MIPS programs. So you should be able to write more interesting, more generic programs. And somehow, again, as I mentioned, this would be useful for your project, the stuff that we'll talk today. Before we start, do you have any question? Do you need any clarification, anything? Do you want to discuss anything before we start? Yep, sure. Yeah, let's start. So the first thing is about arrays. As you know, for most operations, at least for most functions, most mathematical kind of operations, to solve problems, we need arrays, and arrays are useful data structures to be able to handle, specifically also useful anyway for to also be able to somehow have arrays as a data structure in assembly, so we can manipulate, for example, the numbers or the stuff that we keep in the arrays. We are also able to use that as a structured kind of data structure. So be able to somehow create more classes of functionalities that we need to have even in assembly. Yeah, why not? And it's really simple to have this type of data structure even in assembly because of the way how memory works in our machines, right? Again, if you remember, memory is a kind of linear places that we can store, we can load data from. So it's pretty much fits very well the way how memory works in modern computers. So accessing an array means that we need to load the base address into a register, right? So once we have this base address, then we can use the offset to get access to any index in the array and be able to retrieve data from any index in the array and be able to store data inside any index that we want to store, right? So this is one example where this array has, for example, 5 elements, and we have this particular address as the base address, 1, 2, 3, 4, 8,000, right? So again, in hex, this indicates the base address. And we use the whole word, 32 bits, 4 bytes to store the first element. And the next element, the next memory address, you know, by convention in MIPS, since it is byte addressable, the next would be incremented by 4 we discuss it like this will be done automatically at the microarchitecture level, like we know by convention, right? We need to have access to the next memory location after we increment the base address by 4, and as we move on top of this memory address. Okay, so hopefully this is clear. Once we have the base address, you know how to access the other elements, right? For example, if you want to have access to the index number 3, we simply need to basically get offset calculate the offset from the base address. So index number 3 means that we need to move up 3, or in other words, 12 address above the base address, and moving in this location, right? And again, this is in hex, so that's why you see C here for those who can read hex, and you should be able to read hex, right? Any question about this? So hopefully this is straightforward and very clear. Because if you have any question about this, let's discuss it here. I'm sure some of you, which you have not started yet, might not be as clear compared with those who has started and got into more advanced stuff. But please don't be shy. I'm happy to discuss even basic stuff. All of you need to learn, and this is very, very important. At any point, don't be shy to ask any question, so I'm happy to clarify. Okay. And you know that in MIPS, even loading this address is not something that can be done in one single immediate operation, right? So even imagine that we know the exact address, as in this case, and any memory location in MIPS, we know it is indicated by the same 32 bits. This hex number is we need 32 bits to indicate this, and in order to use one of those immediate instructions that we can give immediate address, we know that it is not really possible. And I'm asking why it is not possible after Ross asked his question. Yes.
So I was just going to ask, like, are these addresses for any, like, for an arbitrary data type, or are we like talking about a data type that is 4 bytes? Like, that's how big the data type is that the array is holding. Because if we had like if you know what I'm getting at.
So you mean that there might be some data types that require less than 32 bits, and maybe we don't want to store them in the we don't want to allocate one word for each data type. Is that your question, or something else?
Well, like, so that'd be like 0 to, that represent bytes, right? Like 8000 to, so if we had like a double, if I recall, would that not be like 4 or 8 bytes? Like we wouldn't that need to be 0 to 0, like 00 to 08?
I cannot follow exactly what you mean. So you're referring to this base address, right?
Yeah.
So this is, you know that each of these you need 4 bits to represent, right? For
Right.
each number, okay? So what is your question exactly?
Okay, I think I'm just confused because I was thinking those are bytes, not bits.
Yeah, so these are, for each number here, you need to use 4 bits, right?
Right.
In order to indicate that, right?
Yeah. Yeah, I think I just misunderstood.
I'm sorry, you need 3 bits. 3 bits for indicating for no, sorry, 4 bits. I'm confused with something else. Yeah, we need 4 bits to indicate each of these, right? Because you need to specify from 0 to 15, right? And for that, you need 4 bits in order to specify that, right? Yeah. So again, we have discussed this. That's not a problem. We can use a combination of 2 instructions in order to make that happen. Okay, but what I'm asking now is that, again, I already asked this, but this is like important to get the intuition and remind us why we need to do that. Why we don't have a kind of instruction that we just use the whole address and use one instruction in order to load into a register. And we know that, like, in registers in MIPS, they're able to store the whole word. They have 32 bits to store the whole thing in it. Why, the designer of MIPS, they did not give us any instruction in order to make this happen, to give it 32 bits number such as this and load it into a register. Can anyone elaborate on that, answer that? Any one of you wants to volunteer? Noah, do you know the answer?
Could you repeat the question real quick?
The question is that why in MIPS we don't have an instruction that we can use the whole number 1, 2, 3, 4, 8, 0, 0, 0 as an immediate number in order to put this number into a register. Why we don't have such instruction? I'm not talking about pseudo instruction. I'm talking about hardware implemented MIPS instruction, because clearly there are differences, right? In MIPS, we have discussed that we have several pseudo instructions. These pseudo instructions are essentially instructions that are not directly implemented by the MIPS microarchitecture, but these are instructions that are typically needed by programmers. And we have some example, and once we load the assembly code, if we use a pseudo instruction, even like in Spin, you see that, like, when you load your assembly code, you clearly see some, you do not see one-to-one assignment, right? So you see that some of your instruction has been turned into like totally different instructions. These are the pseudo instructions that that basically will be taken care of not by the hardware, but by the assembler. So this translation will happen automatically. But I'm talking like why we don't have any hardware implemented kind of MIPS instruction to make this happen, and why we need to like use like combination of two, in this case like load upper immediate and or immediate instruction. This is my question. We have already discussed this, but I would like to ask again, so hopefully you fully understand. And again, to remind you, this goes back to one of the two most important properties of von Neumann model. This is connected to one of those two important properties. Should I call some names? Maybe I can, so you can see. I see some names. If I pronounce it correctly, Bella. Is that right? Can you speak? Do you have any answer for this? Can you hear me? Bella Bauranic, if I pronounce it correctly. Okay, so you are not sure for the answer. That's fine. Let me see whether others can answer that. Jacob Randall, do you have any answer for this? If you can hear me. Jacob, are you guys listening?
I'll try and give it a spin. I mean, I'm not sure, but just for the sake of giving an answer, I'll give one. Well, so the upper immediate is loading that constant, right, which is the 1, 2, 3, 4. Mm-hmm. And the lower immediate, or immediate, would be loading like the 800, or sorry, whatever our address is. But I was thinking maybe we don't need to use all of those values at once. Like the load upper immediate would be loading those values because they're not going to be in use. So if they're constant, then we don't we're not using those upper 4 values, but the or immediate would be loading the values that we're using.
But if we are not going to use, why we need to load that, right? So here are the two instructions that we use, right? So we use load upper immediate instruction. So we give this 1, 2, 3, 4, and we give it. We ask, okay, store this number into S0, and then we use or immediate to store the same into S0. Right, so yeah, that's one answer, but is not the correct answer, right? Because I see your point. I see that you say that, okay, like these 4 digits on the left is shared across all of these, and we maybe only need the lower immediate part in order to find the numbers or address the elements in each index, but that's not actually true. Anyone else wants to give it a shot? That's fine if you if your answer is not correct, that's fine. I personally answer like incorrectly many times, so don't be shy.
I have a guess, sir. If
Yes.
you've reached a pause point, is what's happening here that we need to store the piece of information that these data elements are part of an array and then store the data element? Are those the two operations that are happening?
I'm not sure exactly. Can you repeat that again?
Yeah, we're storing two pieces of information.
Correct.
One piece of information is that the following information is entered into an array. It is going to be data stored as part of a composite. And then the second piece of information entered is the actual information that you're entering into the composite.
Not really. So here, again, to elaborate on this, here, like for addressing any data inside the memory, we need to have its address, right? So once we have its address, like we can ask, okay, load this for me, right? You can we discussed this, right? You can ask the computer, go to this particular address in memory and load for me everything it is inside this address. So we definitely need to have the address of anything that we need to get access to. And in this case, like what's happening is that we are somehow trying to put the address into like a register, in this case S0, in order to later on ask that we need to load, for example, the content of this memory. And to give it a very specific example, like here we have an array, like again on the left hand side it is in C. You see that like we declare an array of size 5, and then we multiply index number 0 by 2, and we store it back to the same location. And we did the same for the second element here, right? And here is the corresponding assembly code, right? So here we put the address, the base address of this array into S0, okay? And then this is what's happening in the first two lines. And then we use load word. This is one of the MIPS instruction. And we ask it, hey, like, this is the address of the memory, and this is the offset that we want to have, and put whatever you find in that address in T1, okay, in one of those registers. So we wanted to retrieve the content, we wanted to load the content of a memory address into a register because we wanted to manipulate the data, right? This is like what's happening there. We multiplied by 2, like we do shift left logical, again, like this is what's happening by how we do multiplication in assembly. And then we use a store. Again, for storing word, you need to tell computer, okay, hey, this is the address, this is the data, go and store it there, okay? This is the simple operation we want to do. And for doing that, again, we need to have the address, and the addresses in MIPS, we need 32 bits, okay? And this is what these two operations does. So now what I'm asking is that why we don't have, like, why we have this crazy thing, two instructions to do that. like why the designer didn't give us any instruction that that basically we use that one instruction and load these others into a register in order to do the same. Yes, Ross.
Does it have to do with like decoding it and like, you know, like we need to turn this like obviously eventually like this is like whatever C code, for example, and like it's would be easier to decode if we like had these fragments of the bits designated to certain functions.
Not really. Decoding it. Can you elaborate? Maybe you're getting there.
Like, trying to think about how to kind of like.
Let me help you. Let me help you. Right. So imagine that we have this imaginary instruction X, right? And then, like, imagine that we have something, let's say, let me, or maybe it's easier than, like, let me put it. Okay, let me stop. Very simple. Imagine that we have do you see here? Imagine that we have like some imaginary instruction, xt, right? Whatever, doesn't matter, right? And then we have like, let's say S0, and then we say, hey, 0x1234 8000, right? This is what we want to do, right? We want to use this number. This is exactly what I'm asking. Why we don't have such instruction, xt, is imaginary instruction, right? That we can use the whole thing, the whole number, and load it into S0, and we do the same afterward. Why we need to like split it into two parts and like use LUI and ORI in order to do this for us? So why the designer of MIPS, they did not give us such instruction? This is exactly what I'm asking.
I think I might know now. I think I figured it out, possibly. So the or immediate in the last part concatenates the first chunk of that string with the 4 zeros and then does the immediate with it in order to generate the entire register instead of just half and half. Because MIPS can't handle the 32-bit register with its the op codes and everything else already written in with that part because it's only a 32-bit language.
Exactly, right? You got it right. This is exactly the answer that I wanted to hear, right? So again, to clarify, to explain it, is that one of those principles in von Neumann was that instructions are stored in memory, okay? What is the size of memory that we have in MIPS is 32 bits, okay? We have only 32 bits to encode the instructions that will be stored in memory, okay? I'm the designer of the computer that has 32 bits. Okay, let's do it. So we know that like for encoding the instruction, we need some opcode, right? We need like few bits to encode to decide, for example, like xt is 000. Like imagine that like I want to assign like 3 bits to my instruction. Okay, imaginary again. Not talking particularly about like MIPS, imaginary computer. I'm thinking about like designing a computer, right? With 3 bits, how many possible like function that I can encode? How many? It's clear, right? So we have like 3 bits. We have only from 000 to 111, right? And this is only 8 possible values that I can assign to 3 bits, so I cannot go beyond like 8 instructions, right? And like, hey, like I want more, maybe, yeah, sure, yeah, use more bits, okay? We need some bits to also, we need some part of the memory to also like point to registers, right? So here in this instruction, I'm pointing to register 0, okay? Like how to encode that in computer. Okay, let's decide how many registers do you need. Hey, I want to have a computer, to design a computer like MIPS. I want 32 number of registers. Okay, sure. Then how many bits you need for encoding 32 bits, 32 possible registers or possible variations? How many do you need? Definitely you need more than 3, right? Can you encode it by 4? Can you encode it by like 4 bits? Like it's easy to see how many variation you can count, right? So this is definitely not. You need more than that. You need 5 bits, right? So you need 5 bits to encode to point to different registers. So already I have assigned 4 bits for the instruction and 5 bits for pointing to registers. And definitely I need these for this. And I have only 32 bits, okay? And wow, this is 32 bits, right? So how comes I can put this into a memory location? It's impossible, okay? That's why it is impossible to design an instruction in order to do that, right? In order to make it happen. Okay, and that's why we definitely need, in this case, where we want to load a 32 bits number into a register, and using that number as an immediate, right? As an immediate, we need 2 instructions, right? And like you could say, hey, like why the designers of MIPS did not envision that and did not make the memory size larger so they can use the 32 bits and for memory locations and still like having a larger memory. And again, these are all trade-offs. We'll discuss all of this. Why and I mean this transitioning, like using 2 instructions to load that number instead of 1 instruction is not a bad idea, and it's not very expensive, right? And all of this involve again about the whole trade-off space that we have for designing an architecture. Hopefully this is totally should be clear for you why, right? I want you to understand why, because otherwise this seems very unintuitive, why that might happen. So hopefully this is now clear. And please engage better in the class, answer questions, so we can learn, we can progress. Okay. So this is what's happening. Okay, like, and you say that, okay, maybe somebody, like, if we knew, so if we knew that this number 0x12348000 were in some other registers, like, for example, let's say if somebody, for example, in this particular case, if I knew that somebody already put this number, this address number in T0. Okay, so imagine that we assume that we might have this in T0. Okay, maybe somebody did that before, and we know that that's true. Do we need to still use these 2 instructions to make it happen? Or we could maybe, and we still wants to use the 1 instruction in order to put this address into S0, because we want to use S0 anyway for having as a base address. Yes, we could use T0 as a base address. Yeah, definitely we could use if we know that the base address is already there and like somebody put it there. So I'm asking, like, in this case, do we need to have 2 instructions to move data between like T0 and S0, or we can do it in 1 instruction?
Can you do it with load address?
Yes, I'm asking, like, for example, we want to put this number from this register T0 to S0. Do we have any instruction in MIPS that can make it happen? And like, if so, or more important question is that why that is possible technically? Which was not otherwise possible when we wanted and we needed to use this number as the immediate. So I'm asking, like, whether there is an imaginary instruction that, like, we could use something like this, like S0 T0, something like that.
Could you not add, like, you could just add 0 to a number and then that would set it to it? Like if you added two numbers and one of them, like if you know what I'm saying.
So you mean this?
Yeah.
Something like this?
Yeah.
Is there, yeah, that's it. That's a good point. Is there any other possible way to do that? Do you know any like pseudo instruction to make it happen?
Can you just load immediate or load word?
Load word, like you need to go to memory, right? In this case, like there's no memory access, like it's between registers, right? You know, like we have some, and we had this categorization in MIPS instructions. Some instructions, and this is good to distinguish between like different types of instructions. Some instructions, like you only need registers, right? We need like have access to register, like calculate something, put back to registers and stuff, and like we don't need to have access to memory at all. Some instruction like load word, store word, like we go back and forth between memory and registers, right? But in this case, like we only need like we wanted to move data between registers. The answer is simple, right? So we have like move, if you remember, that make it happen. Move again is basically is a pseudo instruction, but Ross solution is preferred, specifically if you don't want to use pseudo instructions, right? This is one way of moving data between this register and this register, right? And then you can continue the same. You can continue exactly the same stuff. Here, once you move the base address into a 0, okay? So this, again, imaginary scenario was a scenario that we knew that like somebody put the base address into T0. We don't care like how it came, right? Maybe like how that somebody could make it happen. Do you have any thoughts? How this could like, I mean, beside this, like doing this LUI or I, how this number could be loaded up into T0 in some other way. And this is important. I want to discuss this because this is, again, something very important. How on earth this could have happened?
Load word.
Okay, load word, but this, like,
well, I mean, you would load each both, like you would split it up into two words and then load both of those, right?
No. This is I'm not talking about this situation. I'm not, so I don't want to use like these two instructions. I don't like that, right? What is can you imagine any other way that you can use and also like not I mean, this way that somebody put this number into T0 and like we were lucky and like we used that and we moved this number to S0 through this. But imagine beyond this, I don't want to use this. I want to imagine. I want us imagine another way of using one instruction here. I'm not saying instruction that involve immediate, but one instruction that could put this number, this 32 bits number, okay, into S0. Can you imagine any other way?
Hello, can you hear me?
Yes.
Can we do load address?
Oh, load address, okay. Then what it does for us, load address?
That only loads from a label, I guess, right?
So basically, you specifically mean that this load address, right? And if, I mean, like, if you think about it, like you remember we had this simple but useful thing. So again, like anytime that you wanted to look at the whole possibility of instruction, maybe look at this reference, quick reference that I gave it to you, right? I mean, load address essentially use an immediate in order to load an address that is provided by a label, right? I'm not sure how would that be possible. I mean, I see your point, and in general, what it does is that if we know that, like, the address of a label, and you had this in your homework, right? So if you remember, let's go back to your homework. Like we had some stuff here, okay, and you see how we use load address. So we had this data structure, okay. We declared it here and we put stuff there, okay. And then here we use load address to put the address of this data structure, okay, into S0, okay. And obviously, yes, this load a 32 bits address into a register with one line, with one instruction, and this is absolutely a correct answer. But what I'm asking is slightly different, right? So in this case, like we use this label, and this label took care of this translation, okay? Took care of this this translation for us, and we definitely do this if we have, for example, if we want to, for example, declare like an array here, we could definitely do that, and we could, again, this is what we did here, right? This is like some sort of structured data that we load the base address, and then we went through each of them one by one by loading the base address. So this is what it happens here. Like, so here we load the base address, and here we increment it. So each time, like, it is a loop that going through each test cases and load the next one by one in order to execute the whole logic one by one, right? This is what's happening here, and very similar. This is very similar what we need. But what I'm asking here is slightly different. And thanks for mentioning this. This was a very good answer. But my question is that, like, whether beyond this, is there any other possible way that we could have imagined and this is somehow implicitly happened by load address, actually, as a matter of fact, that we could use one instruction to get this, to have this number loaded up into S0.
Could you just not load the word and then sign extend it?
Load word and sign extended.
That gets you to the 32-bit. Like, isn't that what load word is doing anyway?
Yes, so we use load word. That's right. So, like, we want to put like in S0, but where and why? Like where should I like do this?
Well, when you load the immediate, like, that would be the second parameter would be like the immediate, and then that would be sign extended. No.
You mean here? Here you need a basically a register. You need to have a register as basically pointing to the base, and here is the offset that you can use. You are getting there, but I want something very explicit. How this could have happened? How this transition of, like, this number could have happened in some other way, right? You're getting there, and definitely, like, load word is the right instruction to use. But, like, how we guarantee that we can load the right number into S0, and again, to repeat that, we want to load this number. The answer is very simple. We somehow, like, had this in one of the previous discussions that we had. Let me help you. Imagine that that we have, could we have this number somewhere in the memory, the whole number, this number? No, are you answering? You're muted.
I mean, you should be able to, but you wouldn't be able to have it with an opcode or anything. But if you store it separately in the memory, so you're not in the program area, you can do that.
Exactly, right? So in your data area, you could have this number stored, right, in memory, right? 32 bits, our memory is 32 bits, fine. Yes, we have the data area and we store that, okay? Good. So we have this this number, which is, if you think about it, what is this number in our problem, in like the very case that we are discussing? What is this number? Is it like a number, or it has some particular semantics? Think about it. It's easy. Like, whether this is a number we want to like we want to manipulate it, or it has a very particular semantic. And what is this semantic in our case? No, you're muted.
I was talking to myself. Sorry about that.
Oh, no worries.
Well, it's representing where we are in memory, right?
Say it again. Representing what?
It's representing where we are in memory.
Exactly. So excellent. So this is somehow a different number. So this is a pointer, right? Because it's a memory address, but it's still a number, right? It's still a number, but it's a pointer. Okay.
Do we just dereference it then?
Yeah, exactly. Okay. Exactly. So this is a pointer. So like, and somehow have you had the chance to like use or construct like linked list in other languages, right? What is linked list? You have some like pointer, right, to different places in the memory, okay? And this is what's happening, right? So you use this as a pointer, and you save it in the memory, okay? And if we knew that where this data, like you stored this in a memory, and we know its exact address, and we know that the address of this pointer is stored in S1, right? Stored in S1, then we could use this number to load it up, okay? So we load the word. We know that in S1, with S1, I can get to this, and we use load word, and we put it in S0. That's the other way of using one instruction in order to make this happen. But you see the differences, right? So we basically have this number as a memory address somewhere in memory, and like we know that like its address is stored in S1. We simply use load word. We don't need to use this to instruction in order to make that happen, or we don't need to. And this is actually what's happening with LA as well. Okay, so this indirect referencing to the memory. This is how it's happening with LA. Hope this is clear. And again, I'm having this discussion because these are more useful to discuss it in the context, so you can fully see in particular cases why and what are the other alternatives, right? When you write programs, these are very useful to make correspondences. Okay, so here again, once we did that, we use load word. We load the content of array 0 into T1. We use shift left logical to multiply it by 2, and then we store it back. Again, we load the second element. Now we know that, and this is important again, like when you write program, now we are addressing to the first, the second element, right? And that's why you see 4 here, okay? Make sure that you understand and you write it correctly. So if you would have used 2 here or 1 here. I mean, 1 might be like the bet, like one guess, right? That you could use instead of 4. But that's incorrect. And hopefully you see that why this is incorrect. Because again, MIPS is byte addressable, and 1 pointing to somewhere. So again, to make it very clear, let me make it a lot more clear so you fully understand what's going on here. So you won't make that mistake again that I sometimes do myself. So again, this is the memory that we have, okay? And we have the base address 0x12348 000. Okay, and this is where we pointed out for getting the first element of the array. This is where array 0 is located. And when we say that, when we use load word with like, let's say T0 and S0 as a base, when we put 0, this is where it points. But when we if we incorrectly use 1, this is not here. Do you know where it is? This is here. Okay, and that's why it is incorrect, right? So if we do that, this will thinks that you want to load the word starting from here, which is totally incorrect, right? We don't want to do that, right? Because our array 1 is located here and it starts from here, okay? This is how memory works in MIPS, right? So you should be able now to see the exact reason why you need to do that, why you need to increment it by 4 instead, because you have 4 bytes here, okay, and the starting of the memory location that your array 1, the first element, the second element is located is right after starting of byte number 4. So this is byte number 0, 1, 2, 3, and this is 4. Okay, this one. And 4, 5, 6. Okay. Do you have any question?
I have a question.
Yeah, go ahead.
So is that a stack that the pointer is pointing to? Is that like temporary memory to be accessed?
Which one?
Like the array is that like in stack format?
The array is I mean, you could consider it as a stack. You could store an array in a stack, but this is not an stack.
Oh, okay.
For a stack, we'll discuss a stack shortly. If you have time, yes, we have 10 more minutes. But that's a different story. But this case, no, it is not a stack. But we could do the same with the stack as well. We could like use a stack in order to store array. Typically, we don't.
Okay, thank you.
Sure. So this is, again, to make it very explicit, this is byte number 0. This is byte number 1. Okay. This one is byte number 2. And this one is byte number 3. And this one, this guy, is byte number 4, right? And you know that by convention, right? Because MIPS is big endian, right? Would otherwise, if it was little endian memory, you know how the addressing would have worked, right? Do you have any question regarding this? Hopefully this is clear, because it is important, like, to see the clear reason why it is like addressing we did this the way how we are doing it here. So another question. I have another question for you. Could we do the same thing instead of incrementing the offset, that using 4 as an offset? Could we do the same thing in some other way, right? So exactly what I'm asking is that here, like, we load the base address to S0, use offset 0. We have we did this, we retrieved this, and next we did multiplication to 2 and stored it back to the same. And here we use offset 4. Okay. Could we do the same thing in some other way? And why? Do you have any preference? Maybe think about it, like, for a few seconds. And whoever that has the answer, I come back in a second. Anybody has the answer?
Could you not just add 4 between each register? You just add 4 to the register value, and that would work as increasing your register. Say you could save it as like a temporary one, and then just increment it by 4 instead of using the offset and the load word function.
That's the answer. Thanks, Tom. This is the correct answer. Basically, what Noah is saying is that let me make it clear for you here in the code. Is that let's say like what we did is that we loaded into T1 like we use like an offset in the first place, right? So we use, for example, offset 4 and we use the base S0 in order to have access to array 1. Okay, this is what's happening here. Is that instead of this, maybe we could like what particular instruction you want to use for implementing the exact thing that you mentioned?
You could just use add I because you want the unsigned.
Yeah, you can use add I. Like we basically want to add I, whatever it's in self, right? And what 4, right? Is that correct?
It looks fine to me, but I think I'm missing something.
What you're missing? What exactly you're missing?
You have to add it then to the actual address. Oh, the address is S0.
Address is S0, right? So,
but then you have to access that point as well. You don't have the access in there. You don't load.
We are not done yet, right? So we use load word, right? So we want to do the same, right? We want to do exactly the same. But here instead of using offset, we incremented S0. What we do is that we again use S0 as a base address, but here instead of like using offset 4, like use offset 0, right? Because it's already pointing to the second element, right? And why not, right? I mean, we could do the same, right? So these two either doing this or these are exactly the same, and accessing the same memory location. But in this case, I mean, it really depends on your preference, and like again, this is a trade-off. Like maybe this has better readability, specifically when you know the size of your array, right? So you know the exact size, and like you know like start and end. So like maybe like having using the offset is a lot better and make the code much more readable, and we don't need to like do this, you know, use 2 instructions, but these two are essentially doing the same. Okay. So wanted to also discuss this. Okay, that was, I mean, that was a good discussion. It's certainly cleared things up for you. I guess since we are out of time, we'll stop here. What I had in agenda to discuss was also about function calls. This is also useful for arbitrary programs. You know that, like in programs, you typically use functions to calculate something to have some modularity. Like having modularity in programs gives a lot of flexibility to the programmers, but also more importantly, modularity helps to tackle complexity. Okay, you don't want to put everything into one large code. Functionality help you to break it down to some modular logic where you can independently change and you can make your you can solve complicated program. Not only solving complicated program, but also it increases the maintainability of your code, your system that you're writing. And you clearly saw that in your homework, right? So your homework, we had a function as explicitly for implementing whatever we asked for it, but also we had like another main as a function that we use for the test case, right? Where it tests the function that you will write. Another use case of a function is you know that for the scenarios where you essentially need a function explicitly, for example, for calculating factorials, right? So you need recursive functions, which would otherwise would be very complex to implement otherwise. Using function to implement any factorial, using recursive function for implementing these mathematical objects are the only way to go. So there are some very clear benefit of using functions even in assembly, which is really simple. You already had example of it, but there are some details we need to discuss, like where to store the argument, where to return. We already discussed all of these, but having some explicit thing, for example, like not messing around with some registers that you need in some other places. Like for example, in your main, if you call a function, and in this function, if you mess around with some of the register values that you need in your main later on, then things could go wrong. And how we can tackle that, these are some details that we'll discuss next week and are important. Next week, I'm going to also again have some live coding in order to code some stuff together. So I would stay here for a few minutes. If you have any question, I would be happy to discuss. Thank you, guys.
I did have one question I wanted to ask you real fast
Okay.
about something related to the homework. So I've come up with all sorts of with a few different algorithms to do different parts of the code, but I'm having trouble figuring out how to implement them. Most notably, I've come up with a way to get the bit I'm looking for, but I don't know how to implement it in MIPS correctly.
Do you want to elaborate?
Yeah. So right now what I've come up with is I'm going to use like a kind of like a bit mask. I saw in the textbook that's something you can do with the logical and for picking out a single bit. And I was going to try and generate a mask so that the only digit we care about in the binary number is the one that we are set to a 1 in our mask.
Mm-hmm.
The only problem is when the size changes and the index of the bit we're looking for changes. Let's say when we look for one that's 8, but then we look for one that's like 33 or 34 position because we have those longer words and half words. That's where I start. That's where my algorithm falls apart.
Using mask, I have to say, is a very good idea. And this is what you want to do. But one way of thinking about it, maybe you could utilize the kind of fix um, the kind of fixed blocks that you have, right? So, for example, you know that a word is 32 bits, right? Is fixed, and you know that half word is also fixed, and also you know that like bytes are fixed.
Right. I think the longest one that we have is a double word.
Yes, exactly. And maybe think about it. Think about this way that, for example, even uh, with bytes, you can reconstruct all of this, right? Um, so you can put together bytes in order to construct like half word, a word, right?
Okay. So what I could do then is I could basically divide it by 4 to find the spot that I need the digit to go in, and then just append half words to it until I get to the point I need.
Yeah, yeah. I mean, that's a good idea. Yeah.
Okay, I've just been trying to figure that out because I was kind of wondering how I could get. I think one example says it wants position 33 and then position 35 or something. So I was trying to figure out how I can get both of those separate from each other.
Mm-hmm, mm-hmm.
All right, what I was thinking of using was shifting the bit until I got to a certain point.
Yes, yes, definitely, definitely. Um, yeah, that's a good idea. I have to say, that's a very good idea. Um, yeah,
Like if I just started with like a bunch of zeros and then a 1 at the end on the far right, I just shift it left as much as I need until I get to the point I want.
yeah.
So I could do that for double words as well, but wouldn't I need in order to and a half word, I wouldn't be able to and it with a double word, would I? Or would it automatically populate the zeros to the left of the half word?
Yes, exactly. It really depends on what exact instruction you want to use. But you know that like in MIPS, you have some instruction. If you look at the manual, you have instruction that even you can load the stuff at the byte level, right? Um, so for example, if you if you know, and this is maybe would be helpful, like if you know where is your byte, right? So if you look for some instruction, you can instead of loading the whole word, you can load a byte if you know where this byte is located. The same way as you use like load word.
So what you're saying from that is I could come up with some code to automatically load the byte I care about.
Exactly, because that's the most important thing, right? So like when you chunk thing and like when you find like, okay, this is the byte that I want, right?
So I think I figured out kind of what you're saying then. So I could, if I divide it by 8 in order to get to the number of byte that I need, I can just do 3 write shifts in order to get to a divide by 8.
Yeah.
And then from there, I can use that in order to determine what byte of that word I need. Pull that single byte out from the address and then just shift until I get to that digit I'm looking for.
Yep.
Okay.
That's certainly a nice idea. Yeah.
Okay. I've been trying to like figure out how it would work, but I've also run into the problem that I have a bunch of pseudo instructions that I'm trying to get rid of now because I saw the pseudo instructions after I'd already come up with the basic algorithm.
Mm-hmm.
So I need to go through and change that and get rid of those. But so thank you for posting those on the course website.
Sure, absolutely.
Okay, thank you.
Thank you. Good discussion.